All right, today our lesson is on chapter 4.7, multiplication counting principle and permutations. So first, I'm giving you an example where we see that we have a menu. We have 3 choices for appetizer, 4 choices for a main dish, 2 for dessert. And the question being posed is, well, how many different meals can be ordered from this particular menu? So on a small scale, we can draw a tree diagram like we're seeing to the right. Right here we see our 3 choices for appetizer, and then branches off for the main dish, and then branches off for dessert. So we're able to see, if we count all those pathways up, that there's really 24 different meals that could be ordered from this menu. Okay, and that is a nice little segue to the multiplication counting principle. So on a small scale, great, we could do a tree diagram, that makes sense. But if I had a lot more options for appetizer, main dish, dessert, I'd probably need to do it a different way to be more efficient. So the multiplication counting principle says, well, for a process that involves multiple steps, imagine that there's A ways to do step 1, B ways to do step 2, and C ways to do step 3. The total number of different ways to complete the process ends up just being multiplying that A, B, and C value all together. And that would be the total options, the total number of ways that a scenario could play out. So in our example above, right, remember that we had 3 choices for appetizer, 4 for main dish, and 2 for dessert. We really could have just multiplied that all the way through, 3 times 4 times 2, and we could get to that 24 a bit faster. So again, small scale, that tree diagram makes perfect sense, but if we're given a lot more options for different things, we want that shortcut. We want to know about the multiplication counting principle to get to that answer faster. All right, a few more examples. All right, example 2, we're looking at passwords. So a 5-character password contains letters A through Z and digits 0 through 9. So letters, we know that means that there's 26 total, and digits, that means we have 10. So scenario A, we're saying we can repeat our characters. How many passwords are possible if we have 3 letters followed by 2 digits? So I usually lay out my 5 tiles, and then I mark it that we're looking at 3 letters and then 2 digits just like that. And since we're saying that letters can be repeated and digits can be repeated, well, then I have 26 options for that first position, and then another 26 for the second, 26 for the third, right? Those are all my letters. And then digits, I would have 10 times 10. Okay, a faster way to get there, multiplying it out, right? I can type it in just like this in my calculator, but I can also see that that's really 26 to the 3rd power times 10 squared. So sometimes it's faster to type it in that way into the calculator. Our final answer ends up being 1,757,600. So this is the amount of passwords we could create given these constraints. Okay, for B, we're saying, well, now we just don't want repeats, but the scenario otherwise is staying exactly the same. So no repeats, but we still want the 3 letters and the 2 digits. I'm just going to acknowledge that it's saying no repeats, no duplicates. Okay, so now my letters, I have 26 for that first spot, but now I have 1 less choice for the next position because I've already allocated a letter A through Z in this first spot. So now I have 25, and once I have a letter in that spot, now I have 1 less for the next position right there, so 24. Okay, same thing plays out for the digits, right? I have 10 options for the first digit spot, but in the next position, I have 1 less because I've already put some digit down in this spot first. So now 9 right here. Okay, multiply all of that out. We get 1,404,000 possibilities. Okay, we have 2 more that are also very similar. Let me start the sliding up to here. All right, so now I'm saying, well, we can repeat again, back to being able to repeat, but we still have 5 characters. How many passwords are possible if we have 5 digits? Okay, we can repeat, and they're all going to be digits. All right, so I have 10 choices for the first position. Same for the second, third, fourth, and fifth, because again, we are allowed to repeat. So here it's simple. I can just type that into my calculator, 10 to the 5th power, and I get 100,000. Okay, one more example where we cannot repeat, no repeats, no duplicates. Just write that off to the side. So again, we have 5 characters. They're all digits. But again, I'm saying we cannot repeat this time. So I have 10 choices for that first slot. But let's say that my first position is a 0. I can't reuse that. So now I have 1 less to choose from here, and then 1 less to choose here, and so forth, all the way down to that last position. And when I multiply that out, I get 30,240. All right, example 3, pretty similar. Online passwords help protect confidential information. One website allows users to choose a password that can consist of capitals, lowercase letters, digits, or any of the 4 special symbols that we see listed right here. The only other requirement is that the first character of the password must be a letter. How many different 5-character passwords can be created? So this one, it's similar to the ones above. It's just a little bit more complex in allowing you to have more options available. So I'm going to lay out those 5 tiles again, and I'm just going to think about how many capital letters do I have? Must have 26. How about lowercase? Still 26. We have our digits now. Still 10, and then those special symbols as options 2, we have 4. Okay, so we're seeing that collectively we have 66 total characters that we're using in this scenario. Okay, and our only restrictions are that that first position has to be a letter. All right, everything else can be any character. So here, that first position has to be a letter, so it can be a capital or lowercase. I have 52 options. And then any character for these spots, and it doesn't say anything about not being able to repeat, so that means that it could be any character here. We could have duplicates. Same thing here, here, and here. A quicker way to get to our answer is to say 52 times 66 to the 4th power. So that ends up being a big one, 986,686,272 total options. All right, one more multiplication counting principle problem. So here, looking at license plates, specifically California license plates. Standard license plate for California passenger cars has 1 digit, followed by 3 letters, and then 3 more digits. So we see, okay, that means we have 7 tiles to lay out. Let me start with that. Okay, so the first digit cannot be 0. First and third letters cannot be I, O, or Q. How many possible license plates are there? Okay, so first is a digit, so I'll put a little D there for digit. Then we have 3 letters and then 3 digits. Okay, reading back through those restrictions, we're saying that the first digit cannot be a 0. So first digit here, right? No 0. Okay, and then we can't have an I, O, or Q for the first and third letters. So here and here, no I, O, or Q. All right, so first digit, we know then 9, because we can't have 0 to start it off. Letters are usually 26, so take out 3 options. Now we have 23. Okay, here no restrictions, so 26. Here, the next letter slot, 23. And then no digit restrictions here, so 10, 10, and 10. All right, so let's say I multiply that through. So 9 times 23 times 26 times 23 times 10 times 10 times 10. Could have used exponents as well. Here I'm going to get 123,786,000 total possibilities. Makes sense? California, we're a big state. All right, so good practice with multiplication counting principle. Let's flip it over and let's look at permutations. All right, so permutations, we're looking at a distinct arrangement of some group of individuals. So distinct, I often say specific. We're looking at an arrangement of people, items, things where order matters. Okay, usually there's some mention of place, like first, second, third, or position where we're assigning roles, like a president, vice president, secretary. Let me just add that here. So place or position, often mentioned. And what's nice is that permutation starts with a P, so does place, so does position. So place means we're talking first, second, third, something like that. And position means we're giving them roles, like you're my president, and you are my vice president. Okay, we start to see factorial notation show up. So here I'm showing you what it looks like in structure. So n factorial means we're looking at n times 1 less than n, times 2 less than n, times 3 less than n, etc. So n factorial is really the product. We're multiplying the number starting with n and going down to 1. So let me give you an example here. If I said 4 factorial, so if I had 4 people who were standing in a line, right, how many ways could they be arranged? I would have 4 people who could be in the front, and then 3 that are behind that person, and then 2, and then 1. So I start with the 4, and I'm going in descending order down to 1. Multiply that out, we get 24. Okay, one other thing to point out is that whenever we see 0 factorial, that's always going to be 1. Okay, so the next I'm going to walk you through some basic permutations. So in how many ways can 6 runners in a race cross the finish line? Well, that would just be 6 factorial. So 6 times 5 times 4 times 3 times 2 times 1. It's going to be 720. Right, so we have 6 runners that could finish first, and then once that position is decided, now 5 that could come second, 4 that could be third, and so forth. The way that we can do that faster in our calculator is just like this. I can hit 6, I can go math over to probability, And you see it looks like an exclamation mark, but it reads as factorial. So we go down and we get it. We're back to our home screen. So 6 factorial is going to multiply 6, 5, 4, 3, 2, 1, and we get to 720 really fast. Okay, next here we have 7 books on a shelf, right? So it's in this linear arrangement. So this would be 7 factorial. So same idea, right? 7, 6, all the way down to 1. It's going to be 5,040. Okay, how many ways can you create a batting order for 9 players on a baseball team? So we have 9 of them that could bat leadoff, and then 8 that bat second, and then 7 who bat third, and so forth. So just 9 factorial gets us 362,880. So again, the way that we do that in our calculator, I hit 9, I go math over to probability, and it's that 4th choice, 9 factorial. Pretty easy peasy. All right. So next here we get permutations of n objects taken k at a time. So here if there are n individuals, the notation npk denotes the number of different permutations, distinct arrangements of k individuals selected from a group of n individuals. Okay, sounds tricky. It's not that bad. So n here again is our total number of individuals. Okay, and then k is the number that we are selecting. So the number of individuals that we are selecting in our scenario. So let me give you an example. Okay. So let's say that I have a group of 10 individuals. They're entering an art contest, and I want to give prizes for the first 2 places. Okay, so first, second place. My formula says, okay, so start with 10 factorial. So if I'm giving prizes to all 10 of them, it would just be 10 factorial, but I'm only going to give prizes to the first 2. So I'm going to divide away 10 minus 2 factorial. So it's always going to be the n minus k. Here's the n, here's the k. So it ends up giving me 10 factorial over 8 factorial. And when I write that out, that's like saying 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 over 8, 7, 6, 5, 4, 3, 2, 1. That feels cumbersome. I'm going to show you a faster way to write that in just a moment. But what happens is, right, 8 to 8 is just 1, 7 to 7 is just 1. Same with 6 to 6, 5 to 5, 4 to 4, and all the way down. So I'm really just left with 10 times 9, which gets me 90. And when I think about that just conceptually, that makes sense. If I'm giving just 2 prizes, I have 10 individuals that could have finished first, and then 9 that could have finished second. So I'm just multiplying 10 times 9. All right, so let's look at it in these last few examples. So here we have a race with 10 runners. How many ways can 3 runners cross the finish line to earn first, second, and third place? So here we're saying, okay, 10 P3. So when I plug that in, I'm saying, okay, that's 10 factorial over 10 minus 3 factorial. So 10 factorial over 7 factorial. So I know that I'm doing 10 all the way down to 1 in decreasing order, descending order. But really, I just need to show the 10, the 9, the 8. I know that if I just write 7 factorial, I already have 7 factorial on the bottom, and that saves me some time. I don't have to write it all out from 7 down to 1, because I know that 7 factorial over itself is 1, right? These will cancel out, That's a 1-to-1 ratio. So I'm really just multiplying out 10 times 9 times 8 and getting 720. Now, when I think that through, just conceptually, that makes sense, right? 10 of these runners could have crossed first, and then I would have 9. I would have 9 that could cross second, and then 8 that could cross third. So 10 times 9 times 8 gets me that 720. Let's try it with a few more. Okay, B, we have 12 members, and how many ways can they be assigned to roles of president and secretary? So we're giving 2 positions here, right? Permutation is place or position. So out of the 12, we're selecting 2 of them for specific roles. So 10p2, so 12 factorial over 12 minus 2 factorial. So 12 factorial over 10 factorial. So again, I can just write out what I need. I need the 12 times 11 and then 10 factorial over 10 factorial. I know that I don't have to write out the 10 all the way down to 1 because it's going to cancel away. Anything over itself is a 1-to-1 ratio. So I'm just multiplying the 12 times 11 and I get 132. Okay, think that through again. I have 12 members that could be president. Once that position is filled, now we have 11 that could be secretary. Multiply it out. Okay, one last one, and then I'll show you a shortcut as well. All right, now we have an iPhone set to choose the songs of a 15-song playlist at random. Songs do not repeat. In how many ways can 5 songs be played? So here we have 15 total songs, and we're selecting 5 of them to be played in our playlist. So we know that that would be 15 factorial over 15 minus 5 factorial. So 15 factorial over 10 factorial means 15 times 14, 13, 12, 11, and then 10 factorial over that 10 factorial. So the 10 factorials would cancel 1-to-1. So I'm just multiplying out the 15 times 14 times 13, 12, and 11. And I end up with 360,360 total ways we could create this playlist. Okay, once you guys show me that you can do it by hand, then I'm going to let you start doing it with this shortcut. So here, I can plug in whatever my n value is. Here it's 15. So 15 first in the home screen. Math over to probability. You see the NPR right there, the second choice. And then I type in here the K value we're using. The calculator says NPR. Our textbook uses NPK. It's the same thing. So plug in a 5 right here, hit enter, and we see that same figure show up. Let me do that one more time. So the n value was 15. I go math to probability right there. It's that second choice, right? Same permutation. Right? Our n value is there. We're calling it the K. Calculator calls it an R. That's fine. It's the number of individuals that we're selecting, and we're saying we want 5. Enter, and voila. There's our end result. All right, so today just a good intro to the multiplication counting principle and permutations. We'll pick up on here soon. Have a good day.